planets move around the sun not in circular orbits but they move in the elliptical orbits by keeping sun under one foci. Square of period of revolution is directly proportional to cube of the length of semi-major axis. So it is t square is directly proportional to r cube. So what is the meaning of geostationary satellite? As the name suggests, it seems stationary to an observer who is on the surface of the earth. Hello everyone, welcome to session 2 of chapter 8 Gravitation. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Dear children, in the last session we have studied about the basic concepts of gravitation, and we have studied about what is gravity, the relation between acceleration due to gravity and a gravitational constant. So in this session, let us discuss about few more interesting concepts, and our first topic for today is planets. So planets, we all generally have an idea about what are planets. So planets are nothing but the celestial bodies that revolves around the sun. As we all know, in our solar system, the planets are Mercury, Venus, Earth, Mars, Jupiter, Uranus, Saturn and Neptune. And these planets revolve around the sun in the elliptical orbit. So this is all what we have studied till now. So whatever the theory that were proposed before we accept this heliocentric theory that the sun is in the center and all the planets that are revolving around the sun. So long years ago, astronomer called Ptolemy, he proposed a theory called geocentric theory, where he explained that the earth is in the center and all the celestial bodies that include sun, planets, stars, everything that revolves around the earth, and he named it as geocentric theory. But after the studies and after so many years, it fails in explaining the actual fact. So the theory got rejected. So again, many astronomers came and they proposed their theory. After so many years, Nicolaus Copernicus explained the theory called heliocentric theory, where he explained that the sun is in the center and all the planets are revolving around it in a circular orbits. But the fact is, all the planets revolve around the sun in elliptical orbits. So how did it proved? An astronomer called Tycho Brahe, he spent his entire lifetime in studying the celestial objects, and he collected some data about the axis of rotation, about the positions of these planets in a solar system. But his student called Kepler, he analyzed the data collected by Tycho Brahe and he explained that not all the planets are revolving around the sun in circular orbits, but they are revolving in a elliptical orbit. And he gave his 3 famous laws, and they are named as Kepler's first law, Kepler's second law, Kepler's third law. So our next topic is Kepler's law of planetary motion. So these 3 laws together called as Kepler's law of planetary motion. Let us now study about them one by one. So the first law is about the orbit, and hence the name law of orbits. So what does it state? So it says that all planets move around the sun in elliptical orbits with the sun at one foci. So sun present at one foci, all other planets will move around the sun by keeping it at one foci in an elliptical orbit. So this elliptical orbit motion or revolution of planets around the sun is revolutionized in the study of astrophysics. So he says that planets move around the sun not in circular orbits, but they move in the elliptical orbits by keeping sun at the one foci. Since this law explains about the orbit, so the name is called as law of orbits, and this is the first law stated by Kepler. So let's move on to the next law, second law, Kepler's second law. It is also called as law of areas. So what does this law says? An imaginary line that joins the planet and the sun It sweeps equal areas in equal interval of time. When the planet is revolving around the sun in its own orbit, it sweeps equal areas in equal interval of time. Since it explains about the area covered by planet in its revolution, so the name law of areas. So here, according to this figure, according to second law of motion, the area of A, B and C is equal to area of DBE, since the planet covers equal areas in the equal interval of time. We can conclude the area may look differ here of these two regions, but they are same according to second law of planetary motion. So here what can we observe, that the time taken by the planet to move from A to C is equal to the time taken by the planet to move from D to E. But the velocity of the planet varies here. The velocity of the planet will be greater when the planet is near to the sun when compared to the farthest distance. So, and hence we can conclude area of this region is equal to area of the region DBE, is what second law says. And we are moving on to the next law, that is Kepler's third law of planetary motion, and this law is famous as law of periods. So we can guess now it is saying about the period of revolution of a planet, and hence the name law of periods. So what does it says? It says that the square of period of revolution of the planet around the sun is directly proportional to the cube of the length of semi-major axis of the ellipse. So if this is moving in an elliptical orbit, we'll consider this as ellipse. So this region is the semi-major axis. I'll name it as A. And according to the third law of planetary motion, let T be the time period of the planet and R be the length of the semi-major axis. So this is a semi-major axis. Let us consider this as R. The length of semi-major axis is R. So let R be the length of semi-major axis. Then from the third law of planetary motion, we can write the square of the period of revolution. T is the period of revolution. So I have to write square of the period of revolution is directly proportional to the cube of length of semi-major axis. So here the length of semi-major axis, I have considered it as R. So T square is directly proportional to R cube. So if you remember this expression, you can easily write the statement of Kepler's third law of planetary motion. It states that the square of period of revolution is directly proportional to cube of the length of semi-major axis. So it is T square is directly proportional to R cube. So these are the three laws proposed by Johannes Kepler about the planetary motion, and these three laws, or the Kepler's law of planetary motion, is applicable to all the satellites. So let us now learn what are satellites. Satellites are nothing but the bodies that are revolving around the planets in definite orbit. So any body that revolves around the planet in its own orbit, in a definite orbit, we will call it as satellite. The word satellite is not new to us or not strange to us. We all have an idea about it. These satellites may be a natural satellites, an artificial satellites, and Earth has its own natural satellite. So what are the natural satellites? So natural satellites are nothing but the celestial bodies that revolving around the planets. So for example, the basic example we can take, that is moon. Moon is a natural satellite of Earth, as we all know. So what is an artificial satellite? As the name itself says, it is not natural but it is artificially made, and these are also called as the man-made satellites. So artificially created satellites for our convenience, for our programs or functions which works on our own requirements. So artificial satellites are nothing but the man-made satellites. Earth satellite, we know that the body which revolve around the earth in its own orbit, and we will call it as Earth satellite, and moon is the natural satellite of Earth, and Earth has also got many artificial satellites we have sent into the space to fulfill our requirements. So any body that revolve around the earth in the definite orbit, we'll call it as Earth's satellite. So in the study of the satellites, we must know about geostationary satellites. So what is the meaning of geostationary satellite? As the name suggests, it seems stationary to an observer who is on the surface of the earth. So geostationary satellites are nothing but the satellites which appears stationary to an observer. So what are the examples for this geostationary satellites? An INSAT series. So INSAT series and Apple series, these are the satellites which are geostationary, which appears to be stationary to an observer who is there on the earth's surface. There is another category of satellites called polar satellites. So what is a polar satellite? So these are the satellites that revolve in a polar region. So these are also called as the low altitude satellites because it will be revolving in very less height when compared to other satellites like geostationary or any. So polar satellites are also called as low altitude satellites. So it will be placed at a height of 500 meter above the earth's surface, and generally they are used in polar region. So these satellites located at a region generally above the earth's surface for nearly about 500 kilometer to 800 kilometer, and they usually revolve in a polar region, and hence the name polar satellites. So all these satellites will revolve around the earth with certain velocity. So the velocity with which the satellite will revolve around the earth is called as orbital velocity. So let us now derive an expression of orbital speed of Earth's satellite. An expression for orbital speed of Earth's satellite can be obtained by the idea what we have studied in the previous sessions. Say for example, look at this diagram. I have considered this as Earth, and there is a satellite which is placed above the Earth's surface at a distance of h from the surface, and r is nothing but the radius of the earth. The small r is nothing but the distance between the satellite to the center of the earth. Now here there exists a necessary centripetal force for the satellite to move around the earth, and there also exists a gravitational force between a body and another body. So in this case, the centripetal force is equal to gravitational force. So why so? Since these two are equal, the satellite can revolve around the earth in its own orbit. Now the centripetal force is given by mv square divided by r, which is equal to, so gravitational force of attraction between two objects is given by gmm divided by r square, where r is nothing but the distance of separation between two objects. So now we need an expression for v, that is nothing but the orbital speed. So let us now simplify this expression. We can cancel m and m on both the sides, and we remain with v square divided by r is equal to gm divided by r square, or we can also write this as v square is equal to gmr divided by r square by cross multiplying this. So r and r can get cancelled, and we will remain with v square is equal to gm divided by r. We need an expression for orbital speed. So v is equal to root of gm divided by r is an expression for the velocity of a satellite which is present above the earth's surface. Now from this figure, r is nothing but the sum of h plus r. So this can also be written as square root of gm divided by r plus h. If the satellite is on the surface, we have to neglect the h term, and our expression will become square root of gm divided by r. So here from this expression we can conclude that the orbital speed or the orbital velocity of a satellite is independent of mass of the satellite, because it depends only on the gravitational constant, mass of the earth, and the distance of separation. We can say that orbital speed is independent of the mass of satellite. So whatever the mass of satellite, the orbital velocity can be calculated with this formula, since it is not dependent on the mass of particular satellite. This is about the planets, the planetary motion, satellites, and all the satellites move with certain speed in its own orbit around the earth, and we will call it as orbital speed. We have even derived an expression to find the orbital speed of a satellite. So in the upcoming sessions, let us derive few more derivations, and we will get the solution for many of our questions. So until then, keep learning all of you. Thank you.